And I shouldn't have turned off recording. It should be just, there's nothing that's going to be copyright issues tonight. All right, so here we are, episode 6. After this, we're at the halfway point with 2 field trips. That means, and really, tell you the truth, a cookout or a pizza, whatever we end up doing. The last meeting, which is the 29th, I believe. So really only 3 more Zooms after this. All right. Why is it doing that? I don't know why it's doing that. All right, so episode 6, we'll talk about the field trip update. I'm going to interview Alex Spins, who could be joining us at any minute now. He is getting his PhD at Ohio State in, I wanted Brandon to be here because it's getting it in aerospace or aeronautics or one of those types of engineering. And I'll let him cue me in. He was one of my main guys on my robotics team way back when. And then his little brother was my head builder on the team that won the world championship. So the Spins have done a lot for robotics in Norman. Anyway, I'll be talking to him for about 5 to 7 or 8 minutes about, and you guys can ask questions too, about aerospace, either engineering or whatever he's actually doing. Let's see if that's him. I don't know why it's doing that, but that's a new thing. Okay, so then we'll get into more into pulleys. And like I say, I'll stop whenever he shows up, I'll stop it and we'll talk to him. Talk about mechanical advantage, talk about work. And today I want to get into dot products and integrals. Because that's a big part of work. You can't talk about machines unless you're talking about work. So our calendar, I don't know why it's happening. Is that him? Oh, that's Adam. Hey, Adam. Okay, so anyway, perfect timing. So there's where we're at. And tonight we'll check off Tuesday. So for the field trip tomorrow, Thursday. Hello, Thursday. We're going to meet at about 12. Let's try and meet about 12:50. I don't know why that's doing that. It's driving me crazy. But anyway, I'm getting feedback every once in a while. So let's meet at 12:50 p.m. somewhere in there, and let's meet at this location. I got a map here. So if you blow up OU's campus, there's the stadium. If you blow this up, there's the big meat grinder, right? The building there. We're at, I don't know why it's doing that. We're at North Oak. We're on the South Oak. So I would say, I was thinking we could park and then ride our bikes, but a lot of people don't have bikes and it's very hot. Oh, hey, Matt. Okay, Matt's here too. We got a big crowd tonight. Good. Alex is going to be a good interview. So here's where we meet. There's the clock tower, okay, at the library, if you're familiar with campus at all. And then if you go just south of that, I'm going to turn that off. Okay, now maybe that'll stop that feedback. If you just go south of that, you'll see the physics building. It's called Nielsen Hall. But I've circled in yellow where I want to meet. Somewhere on the east side, which is like the front, the south oval side of those physics buildings, right here, at this location right here, in that green circle, you can look in the window. There's a big plate glass window there, and they have a Foucault pendulum in there that's always going 24 hours a day. So it's really cool. And you can, if you haven't seen it yet, we can talk about that while we're standing around waiting for everyone to show up. And then the professor will meet us out there and then bring us in, and then we'll start the tour. And so if you get there by 12:50, if you're running late and something happens, text me my number. Give me my number if there's trouble. My number is 404 5. This is being recorded, but it's only on our private group, 760-8425. So call me if you're, or text me if there's something going wrong and you're not going to make it by 12:50. Now I only have room for, I told them I'd bring about 8 or 9, and that's about what we got. So everybody that has told me they're going, if they go, we're cool. If they don't go, I got people to put in your place, but let me know. All right, who has questions about Thursdays? We're not going to meet tomorrow, but Thursdays feel. Oh, let me open up the. I'll open up the chat. Anybody have a question about Thursday's field trip? Thursday. Okay, Alex is not here yet. All right. If you have a question tomorrow or Thursday morning, just text me or message me or something. Okay, so we will not meet Thursday. So we'll meet at 1 and we'll be done by, if you can hang out till 2, that'd be great. If you it may go till 2:30, but it shouldn't ever go past that. But it's a good chance if you're going to go to OU, it's a good chance to get introduced to, or introduce yourself to professors. It's good they have a face of the name. They're humans like we are, and they remember you, and then you're the one they'll pick to be the whatever, their assistant. So half of life is just showing up, right? So by 2:30 we should be done for sure. Adam and I got some business after that. Other than that, you guys will take off. Oh, Adam said, did OU still have it? Oh, Adam asks a very good question. Does OU still have a mask requirement? And the answer to that is no, officially, but thanks for saying something, because he said that it's about half and half of the people in the building that wear masks anymore. So probably a good idea to bring along a disposable one, stick it in your pocket, and in case some professor or some lab person is freaking out, which they shouldn't be, but by now. But then again, a lot of you guys haven't had your shot yet. So I could see them wanting you to have a mask. So probably bring a mask. I'll try and remember to bring some extras for you if you forgot them. Okay, good question. All right, let's keep going. Okay. Today's interview, as I talked about, is with Alex Spence. That's with him when he was in Iceland. He's the guy with the yellow cap on. The Spence family's a pretty important family in Norman. They do a lot of good things. But anyway, so he will be here. He'll try and get here later on between 6:45 and 7:15. So he's chiming in from Ohio State. And the reason why I wanted to interview him is he's doing some research on air movement, where they're forcing air to oscillate and using that. They're not sure what the application is going to be, but a lot of times your research is ahead of application. And so I thought that was fascinating. And so I want him to explain that to me and maybe talk to you a little bit about his route, how he got there. There is a new addition to the Facebook group, and this is where we do the sheets. I added a sheet. That's sheet number 3. Now, I'm not going to assign anything from that sheet. It's just more practice at incline planes and pulleys. And so on that note, since I'm not going to really assign, I went ahead and also included the key. So I maybe pick one of the 4 and try it, and then just look at the key and see. I'm sure there's a help video somewhere. And then, that's number 2. Okay, these are backwards, of course. And then I also added number 4 and 5. And 4 we'll talk about tonight, and that is on work, just to give you something to write on or something to refer to later. And I'll also post that key as soon as we talk about a sheet. I'll go ahead and post a key, just for your own edification. And then also on sheet 5, that's also on work, talks about dot products and all that kind of stuff. Okay, so and I'll post a key on that once we're done talking about Okay, I just showed you that. Oh, and then something else new. This just came up about an hour ago. I finally input this. We did this last time. That's sheet 20, side 21 of the equation sheets. Here's side 22. And side 22 has, for your convenience, the standard model for particle physics, since we spent some time talking about that, because we were talking about gravity and where we learn all this stuff. And then there is the 5 rules of pulley land. And these reference sheets will be there forever for you. And there's a little bit on IMA, AMA, or IMA, which we'll talk about tonight again, as we're getting into more machines. There's something, full-fledged, holding nothing back work problem on inclined planes and pulleys, about as hard as it gets. Also has a Villator shortcut there, as we talked about last time. And then this is something we're going to talk about tonight, this work. So I'll leave that for a little bit. But those are your two new sheets. We're up to slide 23 now. My goal, I've already got 24, 25, and 26. That should, if we keep moving, should be in there at least. And I'd like to get up to 30. The last few I may just throw in, because you'll have it. It'd be nice to have 30 sheets in front of you or available to you when you're off to college or next year in AP physics. So we're still on pulleys and machines. Okay, we did that. And then we talked about ideal mechanical advantage, and we said with pulley systems or simple pulley systems, it's just the number of what they call load-bearing ropes, which on a simple pulley system, it's all one rope, except for the rope you attach to the ceiling with. So the pulleys are still out in my car, but I'm showing you pulleys here. So the rope, if it's one rope that wraps around those pulleys, that's considered a simple pulley system. And so you can reduce your load like this. The standard load's 100 pounds. You can reduce your load by the number of load-bearing ropes. And so I said, well, in this first case here on the left, there's only one load-bearing rope. The other rope is giving you just a direction advantage. On the one on the right, there's 2 load-bearing ropes. So now it's only 50 pounds, assuming there's no friction in the pulley and no mass on the pulley. And we ended last time talking about this, talking about simple pulley configurations. So if we go through here, this one has an IMA of 7. Now that's all, that red rope, that is all one rope. But what you do is you go along and you count how many of these ropes are supporting the weight. And so there's 1, 2, 3, 4, 5, 6, 7 ropes. You say, no, Mr. Askey, there's one rope. I agree, it's one rope, but there's 7 sections that are all supporting that 100 pounds. So whatever 100 divided by 7 is, 15, whatever, you wouldn't take much to lift that 100 pounds. Here, this one, you go, well, that's not quite as good, but really it might be better. Here I go, 1, 2, 3, 4, 5, 6. LBRs. This has 6 load-bearing ropes. And why didn't I say 7? Why didn't I include this purple one here, this purple section? Anybody want to hazard a guess? Why didn't I include the purple section of that run rope? That's, by the way, that's where I'm pulling. I'm pulling down right there. So why not include it? I mean, I included it over here on the 7, with a 7 load-bearing ropes. Why didn't I include the purple section? Oh, Jacob said it's not load-bearing, and that is true because I'm pulling down on that section of rope, and so it's not really helping lift it. But what it is helping is it's giving me, as we said last time, that's giving me a direction advantage. And that's pretty important. I'd much rather pull down on a rope than lift up on a rope, just muscles. And when you pull down on a rope, you get to use gravity to help as an assist. Now over here, this one, we are, oh, right. I was asking them on this one too. I gave them a pulley system. I said, okay, now show me something with an IMA of 5. And so they had to show me 5 load-bearing ropes there. Okay. Now let's look at this one. Okay, we talked about that. So now here's a couple of examples that we had set up in room 807. And my question is, if you can tell, here's the load. Here's the load. Let's go this color. Here's the load right here. And we're pulling down with the effort right here. And the question is, what kind of advantage do I have here? Or what's my IMA and what's my advantage on this one, the green circled system, if you can see it. And in class, we then had them go along. We had like 10 stations set up, and they had to go to each station and then, you know, pull and see what they, and then it brought up efficiency, the idea of efficiency. All right, so we got the weight here. That's called it's my load. If you can, let's blow this up. So there's my load, and it's going wrapped around the pulley and then pulling down here. That's my effort. And notice that there's only one load-bearing rope. So if the load was 50 pounds, I'm pulling down with 50 pounds. Let's say it's 100 pounds though. And then in the second situation, that's a practical example of what we're talking about. There is I'd be pulling up with, and in fact, you see it there. If that was 100 pounds, you'd pull up with 50. Now, here's the thing. With machines, all machines come with Pac-Man, as we talked about. Pac-Man is always eating mechanical energy. And we didn't say this, but Pac-Man poops out heat. Pac-Man eats mechanical energy. Now, mechanical energy in physics is useful energy, energy that I can use to move something or do something. That's mechanical energy. Then there's just heat, which is wasted energy. Heat, unless you put it into a piston or something or a chamber, heat doesn't do any good. It heats up the room, but it heats up the molecules in the room. It doesn't run a machine. So it doesn't move anything. So Pac-Man eats, Pac-Man being friction, Pac-Man eats energy, useful energy, and poops out heat. So in this case, that's a pretty good pulley I have there, but it probably has, that's little ball bearings in it, but it probably has, for each pulley that you use, you take off anywhere from 2% to up to 5% if it's a bad pulley. So from your IMA, so you'll lose 2 to 5% every time, every pulley you stick in there. So, and that's called AMA, or actual mechanical advantage. So in this case, looking back on this guy, I have 1, 2, 3, 4, 5, 6 pulleys. And so for every pulley, let's say it's a really good system, and every pulley is like ball bearings and everything else, I'm still losing 2% of my useful work, the amount of work I can get out of it. I'm losing 2% per pulley. So really you're down to 88% efficient, not 100%. And that's when we say it's not IMA anymore, it's AMA, actual mechanical advantage. All right. So I don't want to get too far ahead of myself here. All right, so before we can get into, and remember, we're using pulleys as an introduction to machines. Eventually we get to, stop the share for a second. Eventually we get to a more complicated machine like this 2-stroke engine. Okay, you might find on a weed eater or something. So a 2-stroke engine, right? So there's all kinds of torque involved here. There's chemical energy. There's, but there's all kinds of forces involved. There's no pulley system here, but this is another example of, like an input force, output force, efficiency, how much friction is there in there? You need oil. So that's what we're kind of working our way towards, is to, if you're mechanical engineering or any kind of engineering, you have to understand how an engine works. Okay, so let's talk about work. Now that is, I'll take a screenshot of this, but it's also on the equation sheet. Let's back up for a minute. So I have what I do in class, and we can't really do it here, unfortunately, is I have them, we spend a whole period where they go around and there's like 10 stations, and they have to go through and they have to do these little dumb little things like lift a weight, open a door, step on a chair, just things like that where they're forced to or pull stuff up pulleys. I mean, use a pulley to pull stuff up a ramp. And the whole point is that they're doing work, and what is that work, and trying to get their body into the work. Okay, so since we can't really do that, we can at least talk about it a little bit. So I don't know if you're taking notes or whatever. This would be the time to get that pen and pencil out. I just find that it's really hard to listen to anybody unless I'm writing something down. So probably want to start writing some stuff down. Maybe we'll do a problem or two. In fact, we will. Okay, until Alex shows up. So this is work. Work, which is a W with the oh, sorry. Let me share the screen again. Sorry about that. So work is what I was showing them was this sheet right here, APS.4, which is the one that I said that students can go around and they can work on different stations. But work it's a W, capital W with those hash marks. A W without the hash marks, just W like that stands for watts. Okay, which we'll get to, believe it or not. Watts is a unit of power. So it's kind of used a lot of times when you're talking about machines, you're talking about horsepower or watts. So that's what we have to distinguish, because it gets confusing if you don't distinguish that. So work, that is work, is equal to, simply, it's very simple. It is the force vector dotted with the displacement vector, how far you went. So it's how much force I'm putting on something through a distance. So if I'm pushing a grocery cart at Sprouts, and I'm pushing it down the aisle, and I put on, let's say I'm pushing lightly. So let's say I'm putting on 10 newtons of force, and I go down a 3-meter aisle. That is simply 30 Newton meters of work. Now that's about the simplest example I could think of. That's you pushing horizontally and the cart moving horizontally, okay? There's no special units of work, just Newton meters. There is of energy, and people mathematically, energy and work are the same thing, but as I'll show you, it'll probably be Monday or Tuesday next week. They're different. They're different conceptually. They're the same mathematically, but different conceptually, work and energy. Okay, so that's simple work. It's just, this is, by the way, this is called I'm gonna get into trouble. Woo-wee. I'm opening up all kinds of cans of worms. This is a dot product. Okay. How many of you, give me a thumbs up if you've ever worked with dot products? They used to in, maybe they still do in calculus, but they used to in pre-calc introduce dot products and cross products, which seems pretty important to me. And I've had meetings with the math department and said, why did you guys stop doing that? And apparently they still aren't doing it.
Hey, Askey, whatever you're...
Because all of electromagnetism is either dot products or cross products. And if you're dealing with vectors and you want to multiply vectors, okay, so now let's keep going. I kind of left this optional for me because I knew it was going to get a little nutty. So let's keep going here, see where this goes. So if I want to multiply vectors, this is why you pay the big bucks to be here. is stuff like this, because this is going to give you a big heads up on anybody else in your physics class. But we've talked about adding vectors, right? We've added vectors. In adding vectors, we said there's two ways to do it, right? If you add vectors, you can do head to tail. Now, this is something that, Carson has never heard of, but the rest of you, we've done head to tail, which is a pain, but you can see it does have, hopefully I showed you there are practical applications. The other way is stack and rack, right? Put them into components, I roofs and J roofs, stack them up, and then rack them, add them up. So more accurate, but also more tedious, less visual. So that's adding or subtracting vectors, fine. But now you can also, it turns out, you can take two arrows. It's weird enough adding them. Like we're used to saying 2 plus 3 is 5, but really that's only one possible example. 2 plus 3 could be 4. 2 plus 3 could be 1. It could be all those. It couldn't be 6. 2 plus 3 can't be 6. But that's just weird because you're adding in the angle. That these are air. I'm putting, here you go. Hold on. I'm putting these arrows. Can't see me, but I'm on the small screen. But I'm adding these arrows together. Now, putting arrows like this, that's easy. Just add up the lengths. But when one's at an angle to the other, and we've been through this. That's the whole routine of head to tail and all that stuff. Okay. But now, this is weird. This gets to the point of being just too strange. Now we're going to multiply. Oh, Alex is here. Okay.
Take your time.
Alex?
I got time.
Hey, Alex. Oh, there he is. All right, let's get off this and let's get on to Alex. Let him go on about his way here. Now, hi, Alex. I'm going to, let's see how to do this. I've interviewed a couple of people, and every time I do it, I've got to rethink all this. And hold on. Okay. Alex, I think I can. Okay, you're unmuted. That's good. Go ahead and say something. See if I can hear you.
Can you hear me? Yes.
Can you?
No.
Can you? Okay. No. All right. Hold on. I'm gonna turn this back on. I mean, they may be able to hear you, but I couldn't hear you.
What about now?
Okay, now say something.
What about now?
Ah, yes. Okay.
Okay, cool.
Okay. All right, and it's getting this weird feedback, but all right, Alex. Right now you're in the small screen, and
Right.
I'd like to make you in the big screen more. Hold on. Stop video. Make host. I guess I'll make you the host. Now, I'm going to make you the host, but remember before you leave to make me the host back.
Make you the host back. Okay.
Changing host now. So I'm just going to be.
Host. Awesome.
Now you are the host, right? So let me stop sharing. Hold on. Let me stop my sharing. Okay. So now, go ahead and if you talk, maybe you'll be full screen.
Maybe.
Yeah.
I think it's just. Is it good? Okay.
Cool. Okay. So I'm gonna. Shoot. I wish I wouldn't go back and forth, but anyway, I guess it'll go back and forth. Me talking, you talking. So my question to you, you're at Ohio State.
I'm currently at Ohio State. Yes.
You were at Connecticut though, weren't you?
Yeah. So after graduating high school in Norman North, I went to OU 4 years, did my bachelor's and my master's with aerospace engineering. And then I left for Connecticut to work at Pratt & Whitney doing engineering for jet engines there for 3 years.
Pratt & Whitney. And how was that?
So that was actually really cool because they let me go through what they called a rotation program. So I got to work all different parts of the engineering within the company.
That's
that's
cool.
Everything from the repair side, where we had to essentially we're making instructions for how to fix jet engine parts, And so you get to see all the broken parts come in again, all the way to I got to work with what do they call it? The beginning of the life cycle of the engine. So like concept design for a new engine test rig. So the whole span, beginning of life to end of life.
And you were sort of you were sort of an intern.
So that was actually full-time job, hired, paid full engineer salary, which was wonderful. But it's they do it for all of their new employees because they found that especially for engineers, the more experience they have in all different parts of the company and of the engine, the better that they'll do at their job, no matter what it is afterward.
Exactly. You know the big picture.
Yeah, exactly.
And so you did that for a couple of years?
3 years. Yep.
3 years. All right.
3 years.
And then you go on, well, I kind of like, you want to get more back into the research or?
Yeah, that's exactly it. I wanted to be able to take my career in a more research oriented, or at least a earlier life cycle part of the engine. So actually designing new technologies, new system processes. And one of the great ways to do that is go back to school, go get your PhD or other grad school knowledge. And then when you re-enter, you can go in and say, look, I've got all this research experience now. And much more qualified to take, and practical, which is part of the reason I went to Pratt & Whitney for 3 years after coming out of college the first time. So now I can say I've got the practical skills and the research skills to do this job.
So you're very, very marketable then.
That's the goal.
Yeah, no, I hear you. When I did geophysics for 3 years in Dallas, and I went back to school thinking I was getting a PhD in geophysics, and ended up just decided not to. But that was kind of my idea too. I'd have both fields. Okay, so back to that Pratt Whitney for a second. So were you getting tired of the daily grind, or you just felt like you wanted to be more involved in the creative aspect of it?
As for the reason I went back to school when I did, so a lot of that was just predicated off of I don't want to lose all the information I learned in school. Because you don't use all of that every day at work. You I learned all my partial differential equations, all my calculus in school, and I used it every day. But at work, all the heavy lifting on the math, or not all of it, but a lot of the math heavy lifting has been done by someone with multiple PhDs or whatever. And you're doing the math, but it's a lot more dumbed down, so you make fewer mistakes with it.
So you're kind of plugging and chugging more there.
A little more.
Engineer. Yeah,
you have to know. You have to know what's happening in the background, but they don't want you making like differentiation mistakes or vector adding mistakes constantly, right? So the goal is we've made these processes to cut down on that. But as a side effect, you don't get to use the whole breadth of your engineering knowledge that you learned in school every single day, and so you slowly start to lose it. And so I wanted to go back while my school was still relevant. But after I had gotten enough time in industry to have that experience as well.
I think that's perfect timing, because you're right. If you don't use it, you lose it. And after a while, and then it's really hard to go back. So I
noticed that.
Well, so how long have you been at Ohio State then?
So I just completed my my first full year at Ohio State.
Oh, okay.
So that's
were now, of course, Jeff Terry.
Yep.
You know Jeff Terry?
I hang out with him a few times.
Well, Jeff and I are on this adventure together. He's in North Carolina now.
Okay.
He got a job with a New York City company where he can work. His wife or his fiance is now a resident doctor in North Carolina. So he's there and he's working for a company but he's working in North Carolina for a company out of New York City.
In New York. Nice.
Yeah. Remote. Well, his company is, but he's still in North Carolina. Yeah. Anyway, so for the studio audience there, both Alex and Jeff were key parts of our robotics. Were you guys ever on the same team together?
Only when we were at Norman High. I think there were 1 or 2 robots that we worked on at the same time.
That's a lot of brain power.
Program.
A lot of brain power. The same.
Yeah.
Okay. So I wanted, but what I really wanted to interview you. It's interesting to see your career, but what this interesting idea, and you may not be able to say a whole lot about it. I was talking to your dad about this the other night, but something about how you're doing airflow and you're forcing the air in certain ways and starting to
Yeah.
resonate.
Yeah.
Can you talk? Is that like company secret or?
No. That's a I'll call it a popular research topic right now in the both aerospace industry in general, as well as turbo machinery. And it's this concept is called a fluidic oscillator. Oscillating being the left and right, and fluidic being air being a fluid. And actually, will let me share my screen?
Sure. Oh, I think. Oh, well, let me do multiple sharing here. I have to allow multiple. Actually, you're the host now, so
here I can just share then.
Yeah, you should be able to share.
Should be able to share this one because I can show it a lot better than I can explain it.
Got it.
Right. So here we go. This is probably what my dad was talking to you about. On the left side here, we have kind of an example of what this fluidic oscillator is. And the idea is the air is coming in from the left side here. It enters this chamber, and then as it exits, it's sweeping back and forth. So we call it a sweeping jet as well. And you can kind of get a sense of how it functions. It's kind of sucked to one side. They call it the Coanda effect. And then it goes through these little feedback channels and pushes that inlet flow to the other side. And it because there's one on the other end as well, like it keeps repeating back and forth and back and forth.
And what's the frequency on this thing? Is it?
Yep. So something, let's say 2 inches, 3 inches long, right? You can hold it in your hand maybe. You're looking at about hundreds of hertz. So about 100 times a second. So this is very slowed down relative to what you would get there.
Right.
But the good news is with something that quick, then when you start getting to actual applications, you can kind of assume that it's averaged out over time, right? You're not getting as discrete of jets. And what that means is with this really wide sweep is it's great for especially things like cooling applications where you want to use cool air to cool down a hot surface. What's got a hot surface? Jet engines.
Exactly.
That's what you want to keep cool. And we do that actually with, this is a picture of a blade here from a jet engine, turbine blade. We put these little holes in it and flow cool air through them because the temperature in a jet engine after you combust is hot enough to melt the metal. So the only way to keep your jet engine from melting is to put slightly less hot air through it all. So the big idea here then is by having this jet sweep left and right, we can get a nice wide spread. You can kind of see that here in the image. And with that, you can start covering a much wider area to cool. So instead of needing all of these little holes, maybe you only need a few of them, and you can save some of that air because all the air, like you were saying, your Pac-Man earlier, all the air that we're pushing through here, we have to have sucked into the jet engine. So that's work we're having to do to suck the air in. And so we want to use as little bit of that air as possible to cool because we want to use them as much of the air as we can in our combustion, and pushing our plane forward.
Yes. So this is an application to like aerospace. Does it have application to other kind of machines?
Yep. So the big ones I know are aerospace because that is my current field. This is still a research topic, an early technology idea for aerospace. So you don't actually have these on your planes or on your engines right now. That's what we're researching for. But where you do find some of these is in your some newer cars in the windshield wiper fluid. Right. So it pulls and it sprays your windshield. If you use one of these, you can get a nice wide spread of that fluid over your windshield. Exactly.
And any kind of fluid, that's just using actual fluid.
That's using your liquid fluid. Exactly.
Yeah.
Exactly.
Higher density, but still same principle though.
Same principles.
Interesting.
So
that's fascinating. And these always have practical applications you didn't realize afterwards. Somebody else figures out another way what to do with it.
Exactly.
So that'd be cool with sound waves too, to be able to put sound out into a room. Like if you, I don't know if that would work because the sound they get attenuated, but just think of speakers.
Part of what when we're studying these is we're trying to figure out what these frequency is, and of course it's not this slow, so you can't just sit there with a stopwatch and count, right? So we actually will put a microphone right next to it, and we can essentially we can pick up the frequency of it. Exactly based on the pitch, we know how fast it's moving back and forth.
That's awesome. Okay, well that's cool. So I'm way over your time. What told you
No, you're fine. You're fine. I got plenty of
hang around.
time.
Okay. Let's see. So if there's anybody in the studio audience here, now this will go out to uh, on that Facebook group that I invited you to. There's about
Yep.
50 or 60 people there. So I think they all probably have access. It's a private. We'll put this on YouTube, but it'll be
Yep.
private. It won't be public. But they will have access to it, and they're like ex-students and physics professors and stuff.
Yeah,
Is that okay?
That's fine.
Okay.
Yeah.
So do you guys in the studio audience have any questions? I know the Brandon was the one that I was thinking would be here, and this is the one time he doesn't show up, but he's the one who's and he'll watch the video, but he's the one that looks and wants aerospace. Jacob Selden is looking at some kind of astronomy or astrophysics or something like that. So
nice.
He's in that same field, and I'm sure some of the others have also and Sophia's looking into physics. So a lot of these people are, and Anthony Yoon had some influence on the NASA on the idea he had or a name he had. So these are all very bright students.
Nice.
Anybody else have a question that you can formulate? You can say it or you can type it in the chat before I let Alex go.
Do I need to do anything as the host? Let me see if I can give host back to you anyway.
Oh yeah, give me the host back. Yeah. I think you just click on my name, then make host. There you go. Okay. All right. Well, if they may have questions, and if they do, sometimes it's afterwards, and then ask me, or they can always put it. Since you're in that Facebook group, they could. I know you don't do Facebook very much, but they could. They could in there ask you a question underneath.
I think
it'll go to you. Okay.
Yeah, I'll check.
Very good.
This week. So
very good. Awesome. Now, anybody else up at Ohio State from the old crowd?
Not I think you would know. Jeff would be the one. There's a few of Kevin and Ray. They're still in Seattle, but a few of
I know
our friend group there. A few of them are in Ohio or in Columbus with me.
And then Garrett Sickles is in Denver, I guess.
Okay, yeah, that's my brother's actually in Boulder right now. Boulder. So.
Oh, he is. He went to Colorado.
Yeah.
All right.
He did. So.
What's he doing?
He's doing aerospace engineering. I think he'll be a senior this coming year.
No way.
Yeah. Time flies. You're getting
old. Does. Okay, so that's cool. That's cool.
Yeah, and he's doing stuff with. I think he's doing some research on GPS tracking and telling if a signal is like spoofed or not, fake GPS signal. And then he also did some working in their. They have like a satellite command and control center where they essentially do or did some, I don't know, at NASA when they sit in front of the big screens and they're talking with their satellites. Yeah, it's essentially something like that where they were doing their satellite communication. He did that a while ago as well. So he's got some cool stuff going on. I'm only a little jealous sometimes.
Well, once he graduates, I got to catch up with him and see what he's doing.
You do.
Okay, Alex, well, thanks for coming.
Thank you.
We'll go back to our boring lesson of vectors.
Yeah, vectors are fun.
But important.
Learn them now because it makes things a lot easier in the future.
That's right.
Have a good one.
All right. Bye-bye. Okay, guys. I know it's sometimes hard to ask questions, but you guys should try and jump in there with questions. I mean, that's life, when you have a chance to ask lots of questions, you don't. And then when you get older and you wish you'd ask those questions, now nobody's there to answer them. I guess I'll still be around. All right. So that was awesome, man. So you see what he did? That was really smart. And that was my idea, was to go get some practical experience, make some money. I guarantee that when he was at Pratt & Whitney, he was making $90,000 a year, at least, or $100,000 a year, probably the time he left, and getting all the benefits. Now he's going back to being research, but he's getting paid, as a grad student and PhD candidate, but not near. I guess you save up your money. That's what I did. I saved up, about $15,000, which was a lot of money back then, to go to school so I could go and end up just becoming a teacher, but which I'm glad I did. But I'm gonna kill this speaker. It's driving me nuts. I'm gonna turn it off again. Okay, so that's a great idea though. Go out, don't try and go all the way through and get a PhD. Come on, man. Go out, get some practical experience, get a BS in physics or get a master's maybe, and then electrical engineering or civil engineering, go out in the field for a while. Then if you really like that research, and you'll know because these companies you work for, a lot of them have an R&D division. And so I started working with the R&D division and I said, these guys, this is cool. I was bored with my job, but that's cool stuff. So then he went on and did it. I went on and said, I'd prefer teaching and influencing people that way. Glad I did. But anyway, that's a good approach. Okay, so we got about 14 minutes for me to see if I can get something about multiplying vectors through your head. So when we multiply vectors, we do it two ways. One is called dot product. And one is called cross product. Dot products in general, and so here I would say, if I was looking at vectors, I would say F, like we said, F dot delta S. But it doesn't have to be a force dotted with a change in position. You can do an electric field dotted with, what's called a operator, a NAMBLA. You could have that looking at a magnetic field and see what the effects are. A cross product is, and I'm sure in the example he was giving us, there were both dot products and cross products in that fluid flow. A cross product is something like R cross F. And so I tell you the truth, I don't like the name dot product and cross product. That's what mathematicians, they're so imaginative. That's what mathematicians call them. A physicist calls this a scalar product. It's a much better name. A scalar product, when you multiply them together, you multiply two vectors together and you get a scalar out, that's a scalar product. Okay, hang on there. This is called, a cross product is called a vector product because when you multiply those together, you get a vector. Okay, I'm sure you're confused now. So let's start off. I want to hit cross products before we leave in June. But for now, let's concentrate on dot products for the next 12 minutes. So a dot product, if I have a force and I'm applying a force, say it's at an angle, and I apply that force through a distance. Okay, and that's also a vector, so we call it delta S. And that force is, let's say it's a constant force applied through a distance. So I apply that force at point A, I apply it at point B, I apply it at point C, apply it at point D, and I keep applying that force. As I'm applying that force, I'm going to make the object speed up, assuming, right? I mean, if it's a constant force being applied to a car, let's say, then I'm going to make it speed up. If I apply a negative force to it, I'm going to make it slow down. That's negative work. Okay, positive work versus negative work. So, okay, come back here. Hold on. Okay. So, let's see if I had everything in this sheet. These are some of my notes I want to make sure I hit with you. So, so basically it's this, and I'm glad I pulled this up because basically it's this. What a dot product is asking is how much do these two vectors agree with each other? How much does this black and white vector agree? Like if they're like this, if one's on top of another, if the force is being applied right, the same, that is a perfect agreement, right? And in that case, you can just multiply the numbers. If this is 5 newtons and this is 10 meters, that's 50 Newton meters of work. If it's like this, if you can see, let me stop the sharing for a second. Okay, so if it's like this, it's getting a little dark in here. Sorry about that. Say this is the force. Poor choice. Let's not use a black one there. Okay, I'll use a red one. It's almost the same. So if this is the force and this is the distance or the direction, say it's your car going along, and now there's this headwind at you that's hitting you, not a tailwind, a headwind. In that case, that force all along that path is hurting you, right? It's not agreeing at all. They don't agree. In fact, they're the opposite to each other. So as that car with that is moving with that, this is the force of the wind, and this is the how far it went. As that car moves through that, all this negative work is building up. Okay. And it's causing you to keep having to add fuel to your car to get you to go, if you even just to maintain your speed, right? Because there's no agreement between the force vector of the wind and the change in position. Here, the other way, tailwind, there's perfect agreement, and you can let off the gas and just your car's still going to move forward, okay, once you get going. Now, what if it's like in between? Say it's like right here. Say it's a plane and you're going along and you have this updraft like this that's affecting you. Then say that goes along like this. So in that case, there's not perfect agreement. It's not disagreement, but you only get a portion of it. So you get a shadow of this red vector on this change on this delta S. So that is a situation where we got to bring in the trig. Okay. So in that case, we have this situation. Here's my change in position. My delta, we can call it delta. I say delta S because that's general, right? But in this case, it'd be delta X. I have some force acting on that. And then I have an angle right here. Theta. So I want remember that's a shadow. It's kind of like having a light up here and you're pushing that light onto from above. And it's like, what will the shadow of that force be on my change in position? So how much of my change in position is being affected by that big blue arrow, a big purple arrow? Only some of it. And that's why we say cosine. And so the work then done by this force is the force. It's the dot product of F dotted with delta X. But another way of saying that is it's the absolute value of the force times the absolute value of the magnitude of the change in position times cosine of the angle between them. And that is one definition of work right there. That is work.
Mr. Askey.
Absolute value of one vector times absolute value of another. Hold on. And I think somebody's trying to ask a question. I'll turn this back on again. Sound issues is such a pain in the tuchus. Okay, Sophia, if you're asking a question, go and ask it.
You're not sharing your screen.
Son of a biscuit eater. I was doing a great job of teaching too. Too much. There it is, the whole thing. Yay. All right. So I think Anthony was telling me that too. Yes. Having to deal with feedback. All right. So let me go back and redo this now. So there's the force I was talking about. This is one of the key concepts in your life if you go into physics or engineering, and I just blew the description. All right. So what I'm saying is that purple vector is the force, and I'm applying that over this change in position. What that means, it's running out of juice or something. All right, so we talk about agreement, and we did see that part where I wasn't sharing the screen. We talk about agreement of the vectors and disagreement. In this case, they sort of agree. The purple and the blue sort of agree. And so the part that it agrees with is the shadow of the purple vector on the blue vector. And that's why we say F delta X cosine theta. Cosine theta. Yeah, okay. Yeah, thanks. You guys are trying to talk to me. It's like, you're not even hearing us. Sound. All right. So let's do an example. The other way to do it is something called stack and molt. But I don't know if I want to deal with that in the next 4 minutes, especially with this speaker about to drive me crazy. All right. So here's what I was showing you. I was saying, how much do they agree? And now let's go to this. See what I got here. Okay, here we go. So looking at that idea of agreement and all, if vector A and vector B are right on top of each other, that's 100% agreement. That's a big dot product, a lot of positive energy. Dot products are associated with energy. Cross products are associated with torque or curl, how much the thing is rotating. And then if they're the opposite, like in this second and this guy right here, that's a big negative dot product, meaning that it's all negative energy. But then if one is like up, like say it's a normal force, sometimes it'll say how much work does a normal force do. If it's on a horizontal surface, the normal force doesn't do any work. In fact, the normal force seldom does any work because by definition, it's always perpendicular to the surface. So cosine of 90 is 0. Therefore, the normal force just hardly does any work. Unless you're in an elevator, that's a whole different ballgame. Okay. So we're down to 3 minutes. Let's see what else I got for you. I'm wrapping some stuff up here. And I've got an audio problem, I see. Thermodynamics. This is thermodynamics. One of the hardest course, and students will get out of engineering in college after they're either the middle of the thermodynamics course or at the end of it. I almost did. It was horrible because it's so, thermodynamics is the study of heat flow, but it's extremely formal. It's not like mechanics where you can, it's all about heat flow and all this kind of thing. Energy flow, basically. Anyway, but work is a big part of thermodynamics and of machines. So I've already talked about all that. Agreement, no agreement. And then I showed you this, but let's skip this part. We don't need to worry about this right now. It's kinematics, but there's the definition of work. That's if it's perpendicular. So it's cosine of theta, and if it's perpendicular, if it's going the other way, cosine 180 is -1, so it makes sense. That's why you say it's absolute value of the friction. A lot of times, of course, kinetic friction is almost always opposite direction of motion. In fact, every case you'll see it's opposite direction of motion. So that'll always be cosine 180. So work done by friction, W sub F, will always be negative, right? It's always going to eat. That's Pac-Man. Like Alex said, Pac-Man will always eat. And the last thing before the fake bell is this thing. We have another suitcase. And in fact, now remember we always talk about suitcases, and work is the biggest suitcase we had. So far we had force as a big suitcase, but work is, and we'll talk about this a little later, work is the biggest suitcase we have. So that looks confusing. Let's just skip it for now. We'll come back to it next time. All right, so next time we'll get into more. Next time we have a field trip, but on Monday of next week, we'll get into work. And I want to bring in cross products as well. So it'll be Monday or Tuesday. And I'm giving you all this big picture stuff. So because when you're dealing with this this screen share, geez, when you're dealing with this is all about work of the piston, work of the expanding gas, work done on the camshaft. I mean, this is all what engines are, is where's the work? Where is the dot products between the input force and whatever you're trying to move? And usually you're moving a rocker arm, or you're moving a camshaft or a drive shaft or something you're trying to either move or rotate. And if you're trying to rotate it, that's cross product. Okay, that's curl. It's called the curl sometimes. Okay, so other than that little glitch of not sharing the screen, I think it went okay. All right, anything else before we try and wrap this thing up? Before I let you guys go, I won't see you again until we're standing in front of the physics building by the South Oval by the Foucault pendulum. It's inside. The pendulum's not outside. You're standing outside, big window, looking in at the Foucault pendulum. Go with a friend, go with one of these people. I think meeting up somewhere is probably even worse. If we try to meet at the high school and then drive, that's crazy. Let's just meet. There should be, it's summertime. There should be parking on the side streets. You can also park in the parking garage, but that costs you money. I'm too cheap for that. I'll probably ride my bike from home, be honest with you. Unless it's too hot. So then I'll meet you out there. We'll do that thing. Our field trip next week is going to be Tuesday. A week from today will be the Stevenson. So think about that one. And Dr. Richter is really good. He'll be giving us that. It's a one-man show. He's really good. He walks all around. And so that'll be good a week from today. And we'll talk about that more later. Let's get this field trip out of the way first. Okay. Okay, so I'll see you guys. Stick around if you have a question.
Thanks, Mr. Askey.
Thanks, Sophia. Bye-bye.
See you, Askey.
See you, Carson.